refusing to make sense. It was a measurement of radiation, taken by a spacecraft that had already flown farther than any human-made object before, should not have been possible. A planet tilted on its side, cold, dim, and seemingly uneventful, was somehow holding onto a radiation belt so intense that it defied the laws physicists thought governed planetary magnetospheres. For 4 decades, nobody could explain why. And then earlier this year, a team of researchers finally cracked it open, and what they found didn't just solve an old mystery. It rewrote what we think we know about ice giants, about space weather, and about a spacecraft that, against every expectation of its engineers, is still teaching us things from beyond the edge of the solar system. This is the story of Voyager 2 and the announcement that just gave one of its oldest secrets away. Before we get to that answer, subscribe to the channel, because we're about to travel from a launch pad in Florida in the summer of 1977 to the frozen edge of interstellar space, and by the end, you'll understand why scientists say this 800 and something kilogram machine, older than most of the people watching this video, might still have more to tell us than almost anything we've built since. Here's where we're headed. We'll start with why Voyager 2 exists at all, and the almost accidental alignment of the outer planets that made its mission possible. We'll follow it past Jupiter, Saturn, Uranus, and Neptune, the only spacecraft in history to visit all for gas. And ice giants. We'll talk about the golden record it carries, a message meant to outlive our entire civilization. We'll get into the slow, deliberate way. NASA has kept it alive for far longer than anyone designed it to survive. And then we'll arrive at the discovery that has planetary scientists rethinking Uranus entirely. Discovery that only became possible because researchers went back, decades later, and looked at Voyager's old data with new eyes. Let's go back to the beginning, because the story of how Voyager 2 came to exist is almost as strange as anything it discovered. A NASA engineer named Gary Flandreau was working on trajectory calculations when he noticed something remarkable once every 176 years. The outer planets of the solar system arrange themselves in a way that allows a single spacecraft to visit all of them in sequence, using each planet's gravity to slingshot toward the next, saving decades of travel time and enormous amounts of fuel. This planetary alignment, sometimes called the Grand Tour, was approaching in the late 1970s. Missed that window, and the next opportunity wouldn't come again until the 22nd century. NASA didn't have the budget for the full 4-planet mission. Flandreau's calculations made possible, so the agency scaled back its ambitions publicly, framing the mission as a more modest survey of Jupiter and Saturn. But engineers built the spacecraft tough enough and smart enough to keep going if the opportunity presented itself. It did. Voyager 2 launched on August 20th, 1977, and Voyager 1, despite the numbering, launched second, taking a faster, more direct route to Jupiter and Saturn. Voyager 2 took the long road, the one that would eventually carry it somewhere no spacecraft had gone before or since. The engineering behind both spacecraft was, by any measure, audacious for its time. Each Voyager carried onboard computers with a combined memory smaller than a single modern text message. And yet those computers had to autonomously execute split-second course corrections during flybys happening so far from Earth that real-time control was physically impossible. Light itself takes hours to cross those distances, which meant that by the time a command reached the spacecraft, the situation it was responding to might already be long over. Every maneuver near a planet had to be pre-programmed, tested, and trusted completely, because there would be no second attempt if something went wrong. A single planetary flyby happens once, at tens of thousands of miles an hour, and it either works or the opportunity is gone forever. For the scientists and engineers at NASA's Jet Propulsion Laboratory, the Voyager missions became something closer to a life's work than a job. Ed Stone, who served as the mission's chief scientist for decades, watched these 2 spacecraft transform our understanding of the outer solar system piece by piece, planet by planet, discovery by discovery, from the volcanic surprise at Jupiter's moon Io-2, the strange tilted magnetic chaos at Uranus. Before Voyager, most scientists assumed the outer solar system would look calm, cold, and largely unchanging the farther out you traveled. Voyager proved almost the opposite at every single stop, revealing a solar system far more violent, active, and unpredictable than anyone had modeled from telescopes on Earth. Each spacecraft carried a copy of the Golden Record, a phonograph disc containing greetings in 55 languages, samples of music from across human cultures, natural sounds of Earth like thunder and whale song, and encoded images of our planet and its inhabitants. It was assembled by a committee led by astronomer Carl Sagan, under the assumption that the chance of the record ever being found by another civilization was small, but not zero, and that the act of trying mattered regardless of the odds. The team that built it faced strange, almost philosophical engineering problems no one had ever confronted before. How do you explain to a species that may never have seen a diagram or heard a human voice what a diagram or a human voice even is? How do you compress the entirety of a planet's music, its greetings, its diversity of language, onto a single disc small enough to bolt onto the side of a spacecraft and durable enough to survive 1 billion years of cosmic radiation? The answer they landed on was etched in gold-plated copper, designed to remain readable for geological timescales long after every language spoken on it has been forgotten by the species that spoke it. Somewhere out there, 2 identical golden records are drifting through the galaxy, carrying a message that will likely outlast the sun itself, and almost certainly outlast every trace of the civilization that made it. Voyager 2 reached Jupiter in 1979, and what it found rewrote textbooks almost immediately. Its cameras captured active volcanoes erupting on Io, one of Jupiter's moons, the first time volcanic activity had ever been observed anywhere beyond Earth. Before that flyby, active volcanism was thought to be something unique to our home planet. Voyager proved otherwise, and in doing so, opened up an entirely new field of planetary science: the study of geologically active moons, worlds that might be warmed not by the sun, but by the gravitational squeezing of a massive planet nearby. It's worth pausing here to appreciate just how little humanity actually knew about Uranus before Voyager 2 arrived. The planet had been discovered by astronomer William Herschel in 1781, using a homemade telescope in his backyard in England, the first planet ever found that wasn't already known to ancient civilizations. The next 2 centuries, Uranus remained little more than a faint blue-green in even the most powerful telescopes on Earth. Its details, its moons, its rings, its magnetic field, entirely hidden behind hundreds of millions of miles of distance. Ancient skywatchers who mapped the paths of Mercury, Venus, Mars, Jupiter, Saturn across the night sky, and built entire mythologies and calendars around their movements, never even knew Uranus existed. It took modern optics, and then a spacecraft capable of crossing the solar system, to reveal that this pale dot was in fact a bizarre, sideways spinning world with its own set of rings, its own family of moons, and, as it would turn out, its own deeply confusing radiation environment. Then came the maneuver nobody was certain would work. To continue on to Uranus, Voyager 2 needed to use Saturn's gravity to bend its trajectory with extreme precision, threading a path that had never been attempted before, using technology that, by today's standards, would be considered primitive. The spacecraft's computer had less processing power than a modern key fob, and yet, in January of 1986, Voyager 2 became the first, and to this day, only spacecraft to fly past Uranus. What it found was strange from the very first moment. Uranus is not like the other planets. It is tilted almost entirely on its side, likely the result of an ancient, catastrophic collision early in the solar system's history, which means its magnetic field and its radiation belts are unlike anything scientists had modeled before. As Voyager's instruments swept past, they detected something that made mission scientists pause. An electron radiation belt far more intense than any calculation said it should be able to sustain. By every comparison to other planets, Uranus simply did not have the magnetic architecture to hold on to that much high-energy radiation. And yet there it was, recorded, undeniable, and completely unexplained. For a spacecraft moving at tens of thousands of miles an hour, with a single, irreversible flyby window measured in hours, there was no opportunity to go back and check. Whatever Voyager 2 saw at Uranus, it saw once, and then it was gone, racing onward toward Neptune, leaving the mystery behind it unresolved for decades. To understand just how strange this was, it helps to think about Earth's own radiation belts, the Van Allen belts. donut-shaped regions of charged particles trapped by our planet's magnetic field, which was discovered by the very first American satellite ever launched. Earth's magnetic field is generated by a churning ocean of molten iron deep in its core, a mechanism scientists broadly understand, and one that has been studied continuously by satellites for over half a century. Uranus, by contrast, offered scientists a single afternoon of data, gathered by instruments hurtling past at extraordinary speed, describing a planet whose magnetic field isn't even centered on its core, and whose entire orientation is knocked over onto its side. Comparing Uranus to Earth was, for decades, like trying to understand an entire ocean current from a single photograph taken during a storm. In 1989, Voyager 2 completed its planetary tour at Neptune, confirming that the ice giant had its own system of rings, discovering the Great Dark Spot, a storm system large enough to swallow Earth, and clocking wind speeds on Neptune that remain among the fastest ever measured on any planet in the solar system. Gusts strong enough to make a Category 5 hurricane on Earth look calm by comparison. It also captured the first close images of Triton, Neptune's largest moon, a world with active geysers spewing nitrogen gas into the near vacuum of space, and an orbit that runs backward relative to Neptune's own rotation, a strong hint that Triton wasn't born there at all, but was instead captured from elsewhere in the solar system, likely dragged in from the distant, icy Kuiper belt. With that flyby, Voyager 2's primary mission, visiting all 4 outer planets, was complete. No other spacecraft has done it since. None is currently planned to. Every image humanity has of Uranus and Neptune up close, every measurement of their rings, their moons, and their magnetic fields still traces back to this one spacecraft, on this one pass decades ago. But the mission didn't end there, it simply changed shape. Voyager 2 kept flying, kept transmitting, and kept heading outward toward the edge of the sun's influence. It crossed the heliopause, the boundary where the solar wind, the constant stream of charged particles flowing from the sun, gives way to the interstellar medium, the material that fills the space between stars. Its twin, Voyager 1, had made that same crossing back in 2012. Together, it became the only 2 human-made objects to ever leave the protective bubble the sun creates around our solar system, a bubble called the heliosphere, which shields the planets inside it from the harsher radiation of interstellar space. Crossing that boundary should have been the end of the story, scientifically speaking. Both spacecraft were already operating decades past their designed lifespans. Their radioisotope thermoelectric generators, the plutonium-powered systems that supply their electricity, lose about 4 watts of output every year. A slow, irreversible decline, with no way to refuel or repair. But instead of an ending, that crossing opened an entirely new chapter. Because for the first time, humanity had instruments sitting outside the solar system's shield, directly sampling the actual environment of interstellar space, something no telescope on Earth, or in orbit, could ever measure directly. As the years went on, NASA's engineers faced a genuinely difficult decision, one that captures the strange, quiet heroism of long-duration space missions. With power dwindling, they had to choose which instruments to sacrifice to keep others alive. Heaters were shut off, risking damage to onboard components in the extreme cold of deep space, simply because keeping instruments running mattered more than keeping them warm. In 2024, engineers powered down Voyager 2's plasma science instrument, the very instrument that had helped confirm its crossing into interstellar space in order to extend the operational life of the spacecraft's remaining systems. Voyager 1's identical instrument had already failed on its own years earlier and been shut down permanently. So this was, in a sense, the closing of one of the last matched pairs of eyes the two spacecraft shared. 4 instruments remained active on Voyager 2. After that decision, continuing to gather data on magnetic fields and particles in the space between stars, it was a trade-off nobody wanted to make, but one that reflects just how carefully this aging spacecraft has to be managed, decision by decision, watt by watt. From a control room over 12 billion miles away, staffed by engineers working with a machine that predates most of their careers, and in some cases, predates them entirely. Then, in a moment that quietly stunned even veteran mission engineers, the team found a way to buy more time. Tucked inside Voyager 2's electrical system was a small reserve of backup power, originally set aside as a safety margin to regulate voltage. Engineers realized they could tap into that reserve. A technical decision that on paper sounds almost bureaucratic, right? But in practice meant the difference between losing an instrument years early or keeping the spacecraft's scientific eyes open a little longer. The decision extended Voyager 2's ability to keep its instruments running, buying precious extra time for a mission that was never supposed to last this long in the first place. As of the most recent tracking data, Voyager 2 sits somewhere around 13 billion miles from Earth, so far away that a single radio signal, traveling at the speed of light, takes over 19 hours to reach it, and just as long to get an answer back. A conversation with Voyager 2 isn't a conversation at all, not in any sense we'd recognize. It's closer to writing a letter, sealing it, and waiting the better part of 2 days to hear if it arrived. And yet, across that staggering distance, using technology from the disco era, this spacecraft is still working. Which brings us back to that 30-year-old mystery sitting quietly in the data. Because in 2026, a team of scientists finally found the missing piece. Researchers at the Southwest Research Institute, led by planetary scientist Robert Allen, decided to try something nobody had really attempted before, comparing Voyager 2's strange 1986 Uranus. Measurements directly against decades of radiation belt observations made much closer to home, at Earth. It was, in a sense, forensic science. Go back to an old unexplained crime scene, to re-examine it using tools and knowledge that simply didn't exist when the original evidence was collected. What they found was that Uranus's radiation belt behavior, the one that seemed physically impossible for so long, looked remarkably similar to something scientists have observed happening at Earth. Occasionally, structure in the solar wind called a co-rotating interaction region sweeps past a planet. These are regions where fast-moving solar wind slams into slower-moving solar wind ahead of it, creating a kind of traveling shockwave of compressed plasma and intensified magnetic fields. Spreading outward from the sun in a slow, rotating spiral, like water flung from a lawn sprinkler, sweeping past whatever planets happened to lie in its path. When one of these events struck Earth's magnetosphere in 2019, it triggered a massive acceleration of electrons within Earth's own radiation belts, dramatically boosting their energy in a way that had only recently been well understood, thanks to a fleet of dedicated satellites specifically designed to watch Earth's radiation environment in real time. A luxury Uranus has never had and may not have again for a very long time. The SWRI team's analysis suggests that Voyager 2, completely by chance, may have flown past Uranus during exactly this kind of event, a rare solar storm passing through the outer solar system at precisely the moment a spacecraft happened to be there to see it. For decades, scientists had assumed those same high-frequency plasma waves would do the opposite of what actually seems to have happened. The old models predicted these waves would scatter energetic electrons out of a planet's radiation belt, causing them to rain down into the atmosphere and vanish. But newer research, informed by direct observations at Earth, shows that under the right conditions, those same waves can do the reverse, accelerating electrons and pumping additional energy into a radiation belt instead of draining it. If that same mechanism played out at Uranus in January of 1986, it would explain almost perfectly why Voyager 2's instruments recorded a radiation belt that seemed to violate the rules. Uranus wasn't secretly built differently from every other planet in the solar system, just happened to get hit by a rare, violent burst of space, whether at the exact If Voyager 2's strange Uranus data was really the result of catching a rare storm in progress, then every measurement it took that day wasn't a snapshot of Uranus's normal. It was a snapshot of Uranus in the middle of a crisis, a brief, violent disturbance that may never have been repeated since, and may never be observed again unless another spacecraft happens to be there at exactly the right moment. Our only close-up data on an entire planet's radiation environment might be based on the one day, in over 4.5 billion years of that planet's existence, when conditions were anything but typical. Think about what that actually means in practice. Imagine trying to describe Earth's weather to an alien civilization using a single photograph taken during the worst hurricane in recorded history, and never being able to take another picture again. That, roughly speaking, is the position planetary scientists have been in with Uranus since 1986. Every textbook chart of the planet's radiation belts, every comparison to Jupiter and Saturn, every attempt to model how Uranus's magnetic field behaves over time, has had to work from that single, possibly distorted, snapshot, because there was simply nothing else to work from. And that raises an uncomfortable question that planetary scientists are only beginning to grapple with. If Uranus's supposedly baseline radiation measurements were actually recorded during an anomaly, what does that mean for everything built on top of that data? Models of the planet's magnetosphere, comparisons to other worlds, even theoretical work on exoplanets with similar characteristics, an entire branch of science may have been quietly built on an outlier, mistaken for the norm, for nearly 40 years. Textbooks have described alive. Papers have cited that intensity as an open puzzle, one of the enduring oddities of an already odd planet. Giants compared to the rocky worlds closer to the sun. None of. That was wrong, exactly. But all of it may have been describing a moment of chaos, as if it were an everyday condition, simply because nobody had any other data to compare it against. It's a humbling reminder of how much of planetary science, even now, rests on single data points gathered during brief windows of opportunity that may never be repeated. This is where the story stops being just about Uranus. It starts being about how fragile our understanding of distant worlds really is. We have visited Uranus exactly once, using instruments that were cutting edge in the 1980s, nearly everything humanity currently knows about that planet's magnetic environment traces back to that one encounter. If it turns out that encounter happened to occur during a rare and violent storm, then in a very real sense, we don't actually know what a typical day at Uranus even looks like. We know what a bad day looks like, and we've been treating it as ordinary for 4 decades. That's precisely why the scientists behind this discovery are pushing hard for a dedicated mission back to Uranus. In recent years, a U.S. planetary science decadal survey identified a Uranus orbiter as one of